Пока ставим на руку, да? Да. Нет, ну как, там может быть вот
можно быть с английским.
Ну ладно, давайте начнем наш семинар. Значит, у нас сегодня короткое планируется заседание, семинар, точнее. Юлия Агеева, она расскажет о своей поездке на Международную конференцию по квантовой теории, поля, физики, высоких, энергий, космологии, соответственно, в прошлом году.
Да.
Наверное, надо немножко, как говорится, быстрее выстраивать такие семинары после поездки, чтобы ну, как-то в прошлом году не вышло.
Да, начну тогда. Рассказывать буду про свою поездку. У меня доклад будет состоять из 3 теоретических секций. Первая секция больше лирическая, какие-то воспоминания о себе расскажу, ощущения от поездки. Вот. Вторая секция будет про доклады, которые были на конференции, несколько штук просто выделил для себя и решил вот сами поделиться. И третья секция будет основной тезис моего доклада, который будет представлен на конференции. Ну, как уже было сказано, на конференции проходила в ОИЯИ, вот в корпусе лаборатории теоретической физики Боголюбова. Это было в середине июля того года, вторая половина июля того года. Хочется тут отметить то, что это была первая поездка куда-либо на конференцию очно после начала ковида, вот, и поэтому это все было немного вообще как первый раз. Вот, здорово было со всеми коллегами очно увидеться, перемещаться большими толпами между докладами, между отелем и лабораторией. Вот характерная фотография, собственно, куда-то мы идем. Далее, как и все обычно добираются до Дубны, ехала я на поезде, и вот у меня очень давнишняя такая мечта была увидеть какой-нибудь такой фестиваль с такими воздушными шарами, и так совпало, что из окна минут 10, наверное, мы вот эту вот картину наблюдали. Тоже здорово. Решила поделиться с тобой. Ну, в самом городе, я думаю, все видели, вот, я в нем очень люблю вот это вот здание проведать. Я в 16 году была уже в Дубне и заметила там вот это здание, вот это раз снова что-то проведала. Вот, и сам город мне нравится, он руками, и самое главное, что он на берегу Волги находится, вот, какая-то большая вода, очень его люблю. Вот, соответственно, там же рядом Ранковское хранилище находится, оно действительно производит впечатление такой большой воды, его еще, оказывается, Московским морем называют, его тоже получилось туда съездить, посмотреть, полюбоваться. И самое главное, чем хотела с вами поделиться, это то, что у меня с Дубной такое теплое воспоминание связано с следующей. Тут плохая прекрасность, но на самом деле это доклад Валерия Анатольевича. В 2016 году вот на такой школе я была, и именно на этой школе после его доклада я подошла к Валерию Анатольевичу и вот спросила, что нужно сделать, чтобы попасть в научное руководство, потому что задача интересная, вот, хотела бы этим заниматься. Вот. И Валерий Анатольевич сказал, что надо походить на курс космологии и феноменологии карты частиц, сдать их, вот, и дальше будет видно. Лирическая часть на этом заканчивается. Дальше я бы хотела рассказать про саму конференцию, какие были секции, какие вот доклады, не то, что я для себя выделила, но просто какие-то, которые запомнились, решила вам рассказать. Конференция сама состояла из следующих секций: квантовой теории, поля, гравитация, коллайдерная физика, атомная структура, КХД, нейтринная физика и неускорительная физика и темная материя, космология. Вот. Но больше всего я сидела, я полностью сидела вот на вот этих вот 2 секциях, доклады там слушала, и мой доклад был вот в этой секции, что логично. Вот, давайте расскажу немного про какие-то доклады, которые запомнились. Вот начну, наверное, с доклада Алексея Александровича Справединского. Он рассказывал про модели очень ранней Вселенной, то, что было перед Генерацией, это довольно близко к тому, чем вот мы с Валерием Анатольевичем занимались. Вот. Но только он в другом стаде это все строил. Собственно, начал он с того, что обсуждал самые последние результаты по ограничению на R-отношения. Вот. И когда мы пользуемся такими ограничениями из наблюдательных данных, мы можем, соответственно, запретить свою теоретическую модель там, или наложить какие-то параметры на ограничения на параметры теории, на параметры Лагранжана. Вот. И Алексей Александрович тоже этим пользовался. Да.
Лариса is not Russian speaking.
Sorry. So I should turn on the English. Okay. So Alexey Alexandrovich told about early cosmological models like bounds, and he and his colleagues built it in framework of Horndeski theory as well as we did it, but he take different form of this Lagrangian function, as well as he decided to consider anisotropic metric. The motivation, as I understand it, for anisotropic metric was that universe in the very beginning, before inflation, must be anisotropic. It's more logical, and then after expansion, after inflation, everything becomes homogeneous, as we know. So this was his setup. In this setup, as I told, he built the bounds model, analyzed stability, and so on. Another interesting talk by Nikita Nedelko about Hubble crisis or Hubble tension problem. I really like this interesting problem. The main idea is that today we can calculate or find the value of Hubble. Today, Hubble parameter from cosmic microwave background information, observational data, and it is given. It is like this value. And on the other hand, one can use distance labs like CPX or supernova and obtain another value of nova day Hubble parameter a little bit higher than this value. So this problem is well known as Hubble tension problem, and Nikita and his colleague try to somehow modify the model, lambda CDM model, and try to I don't know how to say, make this value closer to the value coming from distance ladder method of calculation of Hubble parameter. Okay, another super interesting talk was given by Boris Latosh. He did Fein graph package for Mathematica, where one can consider different processes with gravity. We know that if you take a paper and pen and start to calculate 3 graviton, 4 graviton vertices, you will, I guess, die because it's very tremendous calculations. That is why it's really cool to try teach Mathematica to calculate it for you, to perform and use such calculations in your own problems using Mathematica. Boris take some assumptions, of course. He consider only general relativity, minimally coupled to gravity matter, and simple cases of matter for his package Mathematica. And there are some examples of how this looks like in Mathematica. They teach the computer to I don't know how to say, to take right indices, momentum, and then you can construct the desired diagram. For example, here we can consider to do graviton sketching, and for example consider 4 graviton vertex. And for example, if we consider S-channel, I don't know, I guess, okay, S-channel diagram with 2 incoming and 2 outcoming graviton, it takes only 3 minutes in computer, but when you do it by your hand, it's not only 3 minutes. And the same for this vertex, so only 15 seconds. I think it's a great result, and I guess it's very useful for many areas in gravity and such. And the last talk I would like to share with you is talk by Полина Петрякова. She discussed self-tuning inflation, and the main idea of this talk is that they consider such a model where there is no super fine-tuned small parameters. Like I'm afraid to say that because it's super cool result, but they even discuss that they can obtain small, automatically small lambda constant. Polina discussed many inflation models. For today, we have many theories, and in many of them we can obtain different models of inflation. But they decided to use FR theories, the Stravinsky model, and somehow modify it in order to obtain more natural model of inflation with automatically small lambda constant. So they modify it in this way: add some scalar field, and also work with extra dimensions, not only this one known metric for dimension, but with this tail. Somehow this extra dimensional compactify in future provide our world nowadays, or in inflation it provides the de Sitter space, and also combination of these parameters here can be varied somehow and provide a small lambda term. Okay, now turn to my own talk in this conference. Sorry for Russian slides. The talk was about generation of cosmological perturbations in Bounce model and framework of Horndesky theory. First of all, I would like to remind you what is Bounce model. This is nothing but the change of contraction stage to expansion stage. Somewhere at some moment of time, Hubble parameter change its sign. Scale factor have behavior like this one, so contraction, then expansion. We decided to consider this exotic model of early universe in the framework of Horndesky theory, or frankly safe in some subclass of Horndesky theory, G2, G4, and G3, G4, some arbitrary function of scalar field and its kinetic term. R is Ricci scalar, X is kinetic term of our real scalar field. And also we consider the following metric, which contains background as well as perturbations. Here you can note scalar perturbation zeta, scalar perturbation alpha, beta, and tensor perturbation H, Ij. But alpha and beta are non-physical because then you write down second order action for all perturbation for this metric and for our theory. You find out that alpha and beta don't have time derivative, so they are physical or some constraints, and that's why one can arrive to this two simple and very nice expression for detail perturbation and H perturbation. Here, I should say that we should consider only models where this coefficient only positive during all evolution, because only in this case our model will be stable. Okay, let's talk about some concrete model of bounds in framework of Horndeski. It's really possible to obtain such behavior in framework of our Lagrangian. The parameterization is as follows: that the Laplace function in metric here is a constant, some constant. Scale factor is given here. D is also some dimensional constant, and here some parameter of this solution. We turn to cosmic time. Now T is cosmic time, and then Hubble parameter also have some power law behavior.
Sorry, where is the bounds itself?
Yeah, you're right. It's not all bounds. All interesting things in our theory occur in contraction epoch. So it's only contraction epoch, and then we can see this contraction epoch with bound stage, and then with inflation, dilation, and so on.
Is it some unified solution, or it's just several parts of solution which you glue somehow?
It's some no. I see. We choose such function, step function, and use this solution with the subsequent. Or is not your question?
It's my question. Yes.
Yeah, we take some very specific step function, multiply them on this asymptotic, and in Lagrangian, we multiply the Lagrangian function with this one.
Mm-hmm.
So in minus infinity times, we obtain contraction phase. Then, then these step functions in Lagrangian work so that in plus infinity we obtain another behavior like
Lagrangian explicitly depends on time.
Yes.
Sorry, you mentioned that then you can glue it with the inflationary stage and others, okay? But if you still should glue it to inflationary stage, why do you need this stage at all? I mean, inflation can solve everything.
We think that inflation can solve, for example, initial singularity, and it has
within this idea of culture inflation, you have no singularity, initial singularity.
I see, but first of all, it has also academic interest, or you can omit inflation and directly come from bound stage to kination. Two reasons.
I thought it was the original idea somehow to suggest something different from inflation.
Yes. We can directly come from bounds from contraction to, for example, to initial reheating to kination. Okay, let's turn to coefficients from second order action. As I say, they must be positive all the time through all evolution.
I'm sorry, I didn't understand the whole thing. How do you multiply the Lagrangian, the kinetic terms, if the function is kind of We approximate some smooth
Not simple theta function, very specific function like multiplication of times.
Yeah, but it should go to zero. It should vanish at some point, right? Because it equals to -1.
No.
Theta function from 0 to 1.
Yeah,
Yes.
yes.
So this is kind of smooth.
Smooth transition between different stages.
And do you imagine that this theta function depends in fact on some field which changes, or it just explicitly depends on time
It depends on time and some parameters.
and breaks the general covariance?
Probably it can be realized by introducing some field.
Yeah, but is this a new field or one of these fields?
We use only, or actually we transfer from covariant Lagrangian to adjoint Lagrangian, where all functions depends on time, and all our step functions also depend only on time.
Yeah, but for example, when you study perturbations, you do not vary this.
We don't, we don't think about stages which come after some moment of time. So we consider only a contraction phase. It has very simple form, and we need to have a very simple form of this function on this stage, and all interesting things like generation of perturbation occur on this contraction on large negative terms. In our simple setup, we have also very simple Pavlov behavior of second order action coefficients. These constants are just constants and some numerical coefficient together with he and together with parameter mu, which come from complete form of these functions. After that, I should say that we also take in account that our perturbation must have some speed not greater than 1. In our model, tensor perturbations propagates with unit speed, and scalar perturbations with a speed smaller than 1. Okay, for stability in our model, we need to consider only such parameters. I drop all details here, just show you the conditions. And for strong coupling absence in our model, we have a danger of strong coupling problem actually, because these functions here in second order action for HG actually have a proportionality to this one. And this is nothing but effective Planck mass squared. And if in minus infinity this function as well as G4 runs to 0, this means that we in strong coupling. That's why we also need to take into account this condition in minus infinity. Okay, here we have two problems in our model. First one is that, as I said, for good spectrum, also without any details, for good red spectrum, we need to consider models with mu greater than 1. At the same time, in our model, we need to consider mu smaller than 1 due to strong coupling danger. The solution here is that we can consider time-dependent mu, and in large negative times we have mu smaller than 1, then mu transfer through unity, and we obtain mu bigger than 1 in times where we want to generate initial perturbations. And very important thing here that the exit, horizon exit must be in weak couple regime, of course.
Is it again explicit time dependency like we have right?
Yes, yes. It's also adhered here, for sure.
Where is it? Where is this?
It's some.
Mu enter this function, this parameter of Lagrangian, some power of time or some
External, okay.
Yes. Okay. The second problem is that, as I told you earlier in talk of Stravinsky, that today constraint on our operation, it must be very small. And in our case, we decided to consider such models where some speed of scalar perturbation is very small, much smaller than unity. The same situation we meet in calculation model in Mohan papers. And here we have very I don't know, I think it's very understandable picture, I call it somehow, where one can understand which values of parameters one can take in order to obtain stable, without strong coupling problem, with a good spectrum model of bounds. So these parts of the picture take the ratio of strong coupling energy to classical energy. Classical energy is nothing but Hubble parameter in our model, but it can be time derivative of Hubble parameter or time derivative of scalar field. But the strongest constraints, the strongest conditions we obtain then consider classical energy as Hubble parameter. So for sure, our model isn't in strong coupling regime, then E strong bigger than E classical. For example, in general relativity, your model is okay, then Planck mass is greater than Hubble parameter, for example. But we consider some defying gravity, so strong energy scale is much has a complicated form. The unity value of this ratio is some constraint here. If we consider parameters smaller than unity, it means that we are in strong coupling regime. Next constraint is that then we consider perturbation of initial generation of initial perturbations. We must consider Weber approximation, and this approximation also provides us with another constraint on key parameter. It must be smaller than this value. And last constraint comes from observational data for R ratio, this one. So here you can take some value of here.
I'm sorry, I didn't understand. Phi is the function of ns, and ns equals to 0.999.
Yes.
So chi is like number.
Actually, our expression for this ratio, for R ratio, parameterized as the function of here and the function of ns. ns can be not only this central value, but it has its own error, so we can vary it somehow. ns equals to this central value plus minus some error.
Small error.
Small, but we take it in account. And
yeah, but I didn't understand the graph. So chi,
yes, here we have
you
only
said
one.
chi is smaller
Yes,
than
only
this.
one parameter. Right.
No, you said that chi is smaller than something.
Yes,
Why is that?
smaller this yes, this concept.
What is that? Chi equals to something plus minus something.
I see here this constant, this value is built for, I confuse you somehow, this value built for this central NS.
Okay.
And this ratio built as functions of he and NS. And I need some concrete form of this ratio, then you understand that they parameterize as functions of NS and chi.
I don't understand at all.
This picture.
Sorry, chi equals to this ratio, right?
No, only for the case, only for some specific case, then let me remember.
What is chi then?
Chi is a parameter of scale function.
Ah, okay.
Yeah.
So chi is independent parameter from the NS?
Yes, and this value built only for, as I remember, only for case then mu equal 1 and for some specific value, this some characteristic constraint. I don't know how to explain it better.
So this is the special case when chi equals to some function.
Yeah, with a specific value of this new parameter.
Okay.
But both these general formulas for both this ratio, this one and this one, are parameterized as function of chi and ns. And here we consider some concrete value of ns in this picture, and both this function became as a function only of chi. And this considered for another concrete parameters. I should remember, and I can tell you more precisely about this one.
Yeah, but what are the graphs?
Okay, red line. This is red line is the function for R ratio, and blue line is a function for strong coupling scale, energy scale, and classical energy scale. You can take this NS and some value of chi and obtain good ratio between scales, energy scales, and good ratio below this constraint. I should remember about this parameter. I don't remember now about this constraint.
There should be between red line and blue line.
Yeah. Only this interval of values are good in order to obtain red spectrum and no strong coupling.
Yeah, but when you say strong coupling, is it? I mean, like you definitely cannot work with this ratio equal to 4, or it's kind of.
Yes, it's also not so good, but.
So this is quite, well, depends on what you mean by strong.
I mean, it's not like, you know, like some ratio, and if you above, you have definitely. Or it's like, you know, alpha strong of order 1, yeah, it shouldn't be 10, 1 or 1.5, it's okay, it's more or less okay.
If you even here, everything is good, okay.
Okay.
Yeah. But of course, we want, I don't know how to say, more no strong coupling values, but we also at the same time we want to obtain small r, and because we
Small r is okay. I mean,
above this unity, everything will be okay with no Okay, two results.
Strong coupling. Probably this is the biggest question.
Maybe
yes.
Is
Yes,
this
more or less, yeah.
point when, for example, amplitudes violate the unitarity? It is strongly divided by E.
Yes.
And the boundary of unitarity.
Yes, yes.
So this is already a strong.
Yes, yes, and
if it is equal to 2,
Hmm?
if this ratio equals to 2,
yes, it's a little bit marginal, of course, but
again,
everything will be work.
what is the violation? Well, not violation. Ratio of amplitude to the unitarity condition. Is it 4, 2 squared?
On language of this one.
Yeah. 1/4, 25%. They grow as square of energy.
Next terms in perturbation series will be bigger than previous terms in perturbation series. I can.
But you don't know the coefficient, it could be 0.1.
Yes, we consider only third order, but in our simple model, in our setup, we also can prove that we in our simple setup we can consider full series, full perturbation series, and prove that the strongest condition come from cubic order Lagrangian, and in cubic order Lagrangian we know coefficients. Yes, it works only for very specific form of these functions, but it works. Okay, we built the model of bounds in framework of some subclass of Horndesky theory with red almost flat power spectrum, but our ratio can be arbitrarily small in our model due to the strong coupling problem, due to conditions from this problem. Okay. I think this is the end. Thank you very much for your attention, and I also choose nice photo from coffee break in conference.
Thank you.
Thank you for attention. Any questions?
Could you show the slide? I just want, does that mean that you have a very specific prediction in this model? I mean, if you will not observe some gravitational waves up to r equal to 0.01, then it's definitely not the solution.
Yes.
Yeah, but at the same time, you said that this theory you have a problem with coupling. If you have problem with coupling, you have usually a problem with accuracy in your predictions.
Mm-hmm.
So actually, you cannot say that it's 0.032 or something like that. You have something plus something before the 1, yes, and then you can exclude also. So I mean, you still can you still can be okay within this idea if this r equal to 0.005, say.
Yes, with 0.005.
I mean, below
below,
this
yes,
line.
yes.
If at alpha equal to 1, you expect some, uncertainties, and maybe
Yes.
they're still okay.
Okay, more questions? If there are no more questions, let's send the speaker again.
Спасибо.
So everyone.
Девушка, помните, вы еще говорили, когда была аттестация аспирантов, что можно будет в качестве предзащитной семинара рассказать подробнее вот эту задачу? Потому что я на аттестацию аспирантов не говорила, и
Да.
тоже интересно.
Ну, вот тогда
Если Паша не против будет. Будь здоров, да.